Let's continue now our study of fields. So far we defined what field extensions are, and we learned that those are the main objects of study in field theory. We learned what algebraic and transcendental extensions are. If an element is algebraic, we learned what its degree over the base field is. We also learned what the degree of a field extension is. This is just the dimension of the bigger field when it is considered as a vector space over the smaller field. We learned that the degree is multiplicative. We learned that finite extensions are algebraic. We also learned that if you have a field extension, the elements in the bigger field that are algebraic over the base field are a subfield of the bigger field. Today we are going to continue and study a very important notion called homomorphisms of fields over a fixed base field. So I have written some of these things already, so let me just go through this carefully. So let us take two field extensions, K over F and L over F. So the base field is the same, and we have two fields above it, K and L. There is no containment among K and L, so K and L are just field extensions of F. An F homomorphism of fields between K and L is a field homomorphism. It's not merely a field homomorphism, but it has an additional property that it fixes every element of F. Okay, so remember what a field homomorphism is. It is any ring homomorphism, that's all. There is no additional property for a field homomorphism. But an F homomorphism, so this F is important here, it's more than a field homomorphism. This F refers to the base field for both K and L. It is an F homomorphism if it fixes F pointwise, or in other words, sigma restricted to F is the identity function on F. Okay, so it simply means that sigma of every element of F is itself. It's not allowed to change elements of F. So a couple of quick examples. You take the field Q adjoint root 2 over Q. Okay, so take that to be K and L, and F is K, F is Q, and look at the homomorphism which sends rational numbers to rational numbers to itself. Every rational number goes to itself, but root 2 maps to minus root 2. Remember that every element of K is a polynomial in root 2 with coefficients in Q. So if I tell you what the image of R is for every rational number R and what image of root 2 is, it suffices to completely and uniquely determine what the image of every element of K is, because sigma is a field homomorphism. It should send 2 times root 2 to, I don't need to separately say what it is. It should be 2 times, it should be sigma of 2 times sigma of root 2. That means it should be minus 2 root 2. Similarly, sigma of 3 times root 2 plus 5 and so on. And I claim that that's a Q homomorphism. That's because it fixes R. By definition, every element of Q is fixed. So as an exercise later, we will do this, and you should think about this before that. Any homomorphism of an extension field of Q is automatically a Q homomorphism. So in other words, Q is automatically fixed by a field homomorphism. You don't need to ask for it separately. On the other hand, let's look at another example. Let's look at the field Q adjoint cube root of 2 and omega, where cube root of 2 is a real cube root of 2. There are 3 cube roots of 2. Let's take the real one, and adjoint omega, which is a primitive third root of unity, and if you recall, that's just e power 2 pi I by 3. This is just cosine 2 pi I by 3 plus I sine 2 pi I by 3. And then let's call these fields K, L and F respectively, and let's look at the function from K to K, which sends cube root of 2 to cube root of 2 omega, omega to omega squared, and R a rational number to itself. So later on you will see why I have chosen these particular images. And just like in the previous example, it suffices to describe the images of these generators, cube root of 2 and omega, and tell what the images of rational numbers are, to uniquely determine the entire homomorphism. Then if you think about it, sigma is an F homomorphism of K, F being the rational numbers, because rational numbers are fixed. But it is not an L homomorphism of K, because cube root of 2 is in L, and cube root of 2 does not go to itself, right? Cube root of 2 in fact goes to cube root of 2 omega, which is not cube root of 2. Okay, so cube root of 2 is not fixed by sigma. That is the notation language we want to use. So cube root of 2 is not fixed by sigma. So in order to be an L homomorphism, every element of L has to be fixed by sigma. In this case it's not, so it is not L homomorphism. Nevertheless, it is a K homomorphism. So now I want to do a very important proposition which will describe to us what are the possible images of elements R for an F homomorphism, and that will also explain why I have chosen these particular images for cube root of 2 and omega. So let us take the following statement. Let K over F and L over F be two field extensions, and let sigma from K to L be a field, or rather F homomorphism. So in particular it is a homomorphism of fields which fixes every element of F. Then let alpha be in K and let beta be equal to sigma alpha. This is of course in L. Then the proposition says the irreducible polynomials. Okay, so I'm actually I should write here, let alpha be an irreducible element. Sorry, let alpha be an algebraic element over F. Let us take an algebraic element. I am working in general with an arbitrary field extension which may not be algebraic, but alpha needs to be algebraic. Then beta, which is sigma alpha and which is in L, is also algebraic over F. So image of an algebraic element is algebraic, and moreover the irreducible polynomials of alpha and beta over capital F are the same. So this is a very large restriction on what can be the possible image of an element in capital K. As long as it's algebraic, that restriction applies. So let's prove this. So what we are saying is that image of an algebraic element is algebraic, and moreover its irreducible element must be the same as irreducible element of, its irreducible polynomial is same as irreducible polynomial of alpha. And the proof is very simple. So let fx be the irreducible polynomial of alpha over F. So what do we know? We know that we write fx as a monic, right? Irreducible polynomial is by definition monic. So we can write it like this: a xn an minus 1 xn minus 1 plus dot 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 a1x plus a0. And what do we know about ai's? They are in F for all I, right? Because it is the irreducible polynomial over capital F. So ai's are in capital F. So then we know f alpha is 0 because it is the irreducible polynomial of alpha. That means alpha is a root. So alpha power n plus an minus 1 alpha power n minus 1 plus dot 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 plus a1 alpha plus a0 is 0. So this is an inequality in capital F. Now we'll apply sigma to both sides. If we apply sigma to both sides, what do we get? Sigma of alpha power n, an minus 1 alpha power n minus 1, a1 alpha plus a0 is sigma of 0. Sigma being a field homomorphism, which is a ring homomorphism, sends 0 to 0. This means, and also because sigma is a homomorphism, you can put it inside the bracket and write this as sigma alpha power n, an sigma an minus 1 sigma alpha power n minus 1 plus I'll write one more term sigma an minus 2 sigma alpha n minus 2 plus dot 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 sigma a1 sigma alpha plus sigma a0 equal to 0. Now what do we know about sigma AIs? Since AI is in capital F and sigma is an F homomorphism. What is an F homomorphism? It fixes every element of F. Right? AIs are in F, sigma is an F homomorphism, so it fixes every element of F. In particular, it fixes AI. So now I can rewrite this as sigma alpha power n plus an minus 1 sigma alpha power n minus 1, an minus 2 sigma alpha n minus 2 plus a1 sigma alpha plus a0 equal to 0. So I have just written sigma an minus 1 as an minus 1, sigma n minus 2 as an minus 1, an minus 2 here, sigma a1 as a1, sigma a0 as e0. This is a very simple proof, but it's an extremely important proposition. This means f of sigma alpha is 0. But what is sigma alpha? I have called it beta. So f of beta is 0. So immediately we see that beta is algebraic over f. The first statement is now clear, right? Because f is a polynomial in capital F, x, and beta is a root of it, so it's algebraic over this. Moreover, since f beta is 0, the irreducible polynomial of beta over capital F divides fx in capital Fx. Right? Because it's the irreducible f beta is 0, that means beta is a root of f, and irreducible polynomial of beta set divides every polynomial which has beta as a root. So it divides fx also. But what is fx? Fx is irreducible because it is the irreducible polynomial of alpha. So it is irreducible. That means the irreducible polynomial of beta over f is also f. That completes the proof. Okay. So the proposition saying that if you have an f homomorphism from K to L, an algebraic element goes to an algebraic element, and the irreducible polynomial of both elements are same. And that's a reason why I cannot arbitrarily choose anything I want as an image of cube root of 2 in this example. Because what is the irreducible polynomial of cube root of 2? I will come back to this and write it again, but it is x cube minus 2. So image of cube root of 2 has to be another root of that polynomial. Similarly, image of omega has to be another root of its irreducible polynomial, and so omega squared is a possibility. Okay, so as examples to illustrate this, how limited f field homomorphisms are, f homomorphisms are, because of this very strong restriction on what the image of an element is. So let me do a few examples. First one is, let's list all. So every example here is for extensions of Q. So in these examples, I want to determine how many f homomorphisms are there. So I will give you two extensions of Q, and in each case I want to determine how many f homomorphisms are there. For example, let's take cube root of 2 to let's take square root of 2, square root of 3. Okay, so remember it is supposed to be a Q homomorphism, so Q must go to Q by identity map. It fixes Q, in other words. Root 2 can go to something. Possible images of root 2 are roots of its irreducible polynomial. Remember, root 2 is algebraic, so we can apply the previous proposition. Irreducible polynomial over Q. What is the irreducible polynomial of root 2 over Q? It is x squared minus 2. This we know because it is a root of this, and clearly this is irreducible because it has no roots in Q. So what are roots of this? It has two roots, right? Minus root 2 and root 2. So only possible images of root 2 are root 2 and minus root 2. Are any of them available here? No. Both root 2 and minus root 2 are not in Q adjoint root 3. Okay, this requires a little check. To be precise, we have to check this because Q root 3 is all polynomials in root 3 of degree 1. So it's a plus b root 3 where a and b are rational numbers. There is no a and b rational numbers such that a plus b root 3 is either equal to root 2 or minus root 2. So this I will leave as an exercise for you. Check this. So that means there are no possible images for root 2 in this field. So there are no Q homomorphisms from Q root 2 to Q root 3. That's all. There are no homomorphisms because root 2 can go to either root 2 or minus root 2 and neither of them is in Q root 3. Okay, so that means there is no homomorphism. So the number of homomorphisms is 0 in the first example. What about root 2 to root 2? Here there are two Q homomorphisms, right? One sending root 2 to root 2, the other sending root 2 to minus root 2. As the previous example shows, the possible images are root 2 and minus root 2. In the first example, root 2 and minus root 2 are not here. In the second example, they are there. So I can send it to this. So this is the identity map and this is another map. Remember, I am not specifying what images of Q are because they are supposed to be fixed. So all I need to say is what is the image of root 2. The third example is, let's take cube root of 2 to cube root of 2. So this is the example that we considered earlier. Cube root of 2 has irreducible polynomial. So again, this is the mantra. To determine images of a possible images of an element, look at its irreducible polynomial, find out its roots and see what are the possible elements that you have in the target field. So irreducible polynomial of cube root of 2 over q, it is very easy to check again, is x cube minus 2. What are the roots of x cube minus 2 in some large field, right? In C, for example, are cube root of 2, omega cube root of 2, omega squared cube root of 2. These are the three roots of this polynomial. Because cube root of 2 is a real number, omega is cube root of unity, so this cube root is also 2, this cube root is also 2. So each of them, this cube is 2, this cube is 2, this cube is 2. So these are the roots. But how many are there in this field? Only cube root of 2 is in cube root of q adjoint cube root of 2. Because we know that this is a real field. This is contained in R, whereas omega is not in R. Right? Omega is a complex, purely imaginary number, right? Purely complex number. It's not in R. So there is only one possible image for cube root of 2. There is only one Q homomorphism here, which sends cube root of 2 to cube root of 2. This is the identity map because Q is fixed and cube root of 2 goes to cube root of 2. So this is the identity homomorphism. And one final example I will do is that Q adjoined cube root of 2 comma omega to cube root of 2 comma omega. So here I do have other possibilities. So cube root of 2 can go to cube root of 2 or cube root of 2 omega or cube root of 2 omega squared. And what is the irreducible polynomial of omega over q? I claim that this is x squared plus x plus 1 because it satisfies x cube minus 1, right? Which it's a cube root of 1, so it's a root of x cube minus 1, which is not irreducible, and you can factor it like this. This must be the irreducible polynomial because x minus 1 clearly doesn't have omega as a root. And what are its roots? It's actually omega 1, omega minus omega squared. So omega has two possibilities, cube root of 2 has three possibilities. Omega can go to omega or omega can go to omega squared, and these are independent. What you choose for the first one, namely cube root of 2, is independent of what you choose for omega. In the example that I wrote earlier in this video, I chose one such thing. Cube root of 2 goes to cube root of 2 omega, omega goes to omega squared. You have any number of such things here. So there are a total of, because these are independent and first element has 3 choices, second element has 2 choices, there are a total of 6 Q homomorphisms here. Okay, so this tells you what are the possible images of algebraic elements are. So now let me do another proposition which illustrates when can you construct a homomorphism. It's alright to say that alpha can only go to roots of its irreducible polynomial, but can there be a homomorphism by just sending alpha to any root of its irreducible polynomial, which is sort of what I did in this example. So I'm going to formalize this in this statement, in this proposition. So let K and L be extension fields of F. Let K and L be extension fields of F. Let us choose 2 elements, alpha in K, beta in L, be both algebraic over F. Suppose that the irreducible polynomials of alpha and beta over capital F are same. Okay, so you have, this is the picture. K is here, L is here, F is here, F alpha is here, F beta is here, right, because alpha is here, beta is here. K and L are not necessarily algebraic extensions. The elements alpha and beta are algebraic and their irreducible polynomial is the same. Then there exists, so this completes the previous proposition. Together these 2 propositions are very important for us. Then there exists an F homomorphism sigma from F alpha to F beta such that sigma alpha is equal to beta. So what I am now saying is that there is a map like this, sigma, which is an F homomorphism. That means it fixes F. Every element of F is fixed by sigma and it sends alpha to beta. So this is very easy and let me quickly prove this. Let F in capital Fx be the irreducible polynomial of alpha beta over capital F. Right, hypothesis is that both alpha and beta have the same irreducible polynomial. Let us call that F. Then by what we saw earlier, we know that F alpha is isomorphic to the polynomial ring Fx modulo the maximal ideal generated by F. Capital Fx is a UFD, right? In fact, it's a PID, being a polynomial ring in one variable over a field F. Small f is an irreducible polynomial, so it generates a maximal ideal and that is in fact the field F round bracket alpha. At the same time, we have Fx mod F is also isomorphic to F beta. By what we saw in earlier videos, we have this. And what is this isomorphisms? Here, remember x goes to alpha here. Here x goes to beta. Because this map sends Fx, any polynomial is sent to its evaluation at alpha. This map, if you remember, Gx, under these maps, Gx goes to G alpha on the one hand, G beta on the other hand. So x bar is what I am writing in the residue quotient ring, but its image is just the polynomial x evaluated at alpha. That is just alpha. Here the image is the polynomial x evaluated at beta, that is beta. So now we are done. And not only that, this map this homomorphism, let's call this phi of an element of A is A, phi of an element of F is itself, because again this map sends Gx to G alpha. So if Gx is a constant polynomial, there is nothing to substitute alpha for. It sends that constant polynomial to itself. That means if you now compose this, so I will not and these are inverses, right? By composing the inverse, these are isomorphisms, right? So there is a map like this and there is a map like this. So I can compose the inverse of the first map with the second map to we get F alpha. In fact, it's a field isomorphism. And by composing we get, and this the F homomorphism, in fact I will write F isomorphism we are looking for. So what I am trying to say is that, so let me actually amend this sentence here. The proposition is better than this. There is an F isomorphism. I haven't technically talked about F isomorphisms yet before, but this is exactly the same concept as F homomorphism. F homomorphism is a field homomorphism which fixes F pointwise. F isomorphism is simply a field isomorphism, that means it's an isomorphism of rings which fixes F pointwise. So this is the F isomorphism we are looking for. Right, that's clear, because this is an isomorphism of rings. It sends alpha to beta, because under this inverse alpha goes to x bar goes to beta. So alpha goes to beta and every element of F is fixed. So that is the proof. Okay, and implicitly I have used this proposition to say that there are 6 homomorphisms in this example, q adjoint cube root of 2 omega to q adjoint cube root of 2 omega, because I need this proposition to say that I can send cube root of 2 to any other root of its irreducible polynomial, and I can construct a valid field homomorphism. Okay, so in this video we have looked at a very important notion which described to us when we have two fields above the same base field F, what is the notion of F homomorphism, and once you have F homomorphism, what are the possible images of algebraic elements. So let me end this video here. In the next video we are going to talk about adjoining roots of a polynomial and how to construct splitting fields of polynomials. Thank you.